All right. Will you hit that continue button on that laptop for me? Thank you. All right. Hey guys, we're reading, so we're at level 0, so everybody can concentrate, okay? Yes, sir. All right. Remember, if you don't have page 32 and 33 completed in your packet, this is your last chance in class to do so with us. Yes, sir. Find your book. All right, cool. Double check the cabinets, and if you still can't, just grab. I'll grab you. You already looked at the cabinets. All right. Thank you guys for being quiet. If your neighbors get tempted, just politely and quietly ask them to stay quiet so nobody gets in trouble. Thank you, guys. Gentlemen in the corner, keep it up, okay, please. Thank you. All right, so good morning to both my online and in-person class. We're going to be going over page 32 in our STAAR packet. That is the assessment over matter and energy. So you'll need a pencil. Won't really need a highlighter for this. Go ahead and open up to page 32. That's where our assessment begins. All right. So keep in mind that you are given a periodic table on the STAARS test. You're given both the periodic table and the reference material. This right here, periodic table and the reference. So it wants you to use a periodic table to answer questions 1 through 17, okay? So it wants us to find the symbol. It wants us to find the number of protons, the number of electrons. Ladies, gentlemen, please, thank you. And the number of neutrons. All right, for lithium, oxygen, and chlorine. So we'll point out lithium right here on the periodic table. All right, point out oxygen and chlorine. Now remember, the periodic table gives us everything we need. It gives us a symbol. It gives us the atomic number, which is the number of protons, which also is the number of electrons. And then since we have the atomic mass, all we have to do to find the number of neutrons is subtract the atomic number. For example, 28 minus 14 would equal 14. That's how many neutrons you have. So again, going back to our chart, lithium, right here on the periodic table, has 3 for the atomic number, Li for the symbol, and 6.94 right, for the total mass. So we'll fill in Li for our symbol, 3 for the number of protons, because that's the atomic number, 3 for the number of electrons, because that's the atomic number. And then if you round and subtract, you're going to take 7 minus 3, and that leaves you with 4 neutrons. 6.94, just round that to 7, subtract, and that's your neutron. Oxygen is represented by an O. As you can see, oxygen has 8 as the atomic number. That's 8 protons, 8 electrons. 15.99, so rounded at 16. 16 minus 8 is 8, so that's 8 neutrons. Oxygen, 8, 8, 8. Real easy. And then chlorine is going to have Cl as a symbol, 17 protons, 17 electrons, and 18 neutrons, because chlorine has 35 minus 17, that's 18. Okay. Again, we're using the periodic table to answer all these. The next 3, it wants us to name the element. Well, it gives us the number of protons in each of these, so it makes it real easy for us. Proton number 11 equals atomic number 11 on your periodic table. So go to atomic number 11, sodium. Sodium. You can also write the symbol Na. Next, we have 4 protons, which means the atomic number is 4. Beryllium, Be. And then last, we have 18 protons. So we look at the periodic table. We go to number 18. Oh, it's one of our noble gases, argon. Group 18, our noble gases. Pretty simple, guys. Again, just using the periodic table, it wants us to go to group 16, period 3, and tell us which element is there. So we go to group 16. Remember, groups go up and down, columns, and they're labeled up at the top. So we're going to go to group 16. And it wants us to go to period 3, I believe. Yeah, period 3. Group 16, period 3. Here's our periods over here on the right side. Period 1, 2, 3. So we'll go across period 3. And when you end at group 16, that's our element. Sulfur. You repeat this process, group 14, period 2, carbon. You repeat that same process, right? And you go to group 2, period 4, and you get calcium. Sulfur, carbon, and calcium. You guys are doing great. Thank you. Just keep in mind, you got no phones, and you got 5 pages to read, 1 page to answer. If I see a phone, I'm going to pick it up. Please do not have them out. Looking at you back there in the corner. Y'all know who. Oh, that's fine. All right. Thank you guys for working on it. I appreciate it. All right. Number 10, 11, and 12. It wants us to write down the number of valence electrons and the number of energy levels. Well, we know that the periodic table tells us the number of valence electrons and the number of energy levels. Groups tell us the valence electrons. Look at the 1A, 2A, 3B, 4B. It keeps going all the way. 3A, 4A, 5A, 6A, 7A, 8A. Those, sorry, 8A, not 18. Those are your number of valence electrons. Everything in group 1 has 1 valence electron. Everything in group 13 has 3 valence electrons. Okay? Everything in group 6 has 6 valence electrons. It's that easy. So if it's asking us for the number of valence electrons for potassium, we just need to find potassium on our periodic table. Potassium K. We know that it's in group 1, therefore it has 1 valence electron. Number of energy levels is told by the period that it's in. Remember, our periods 1 through 7 are listed here. So if we're looking for potassium, we go all the way down. It's in period 4. That means it has 4 energy levels. 1 energy level, 2 energy level, 3, 4, 5, 6, 7. And if you think about it, the bigger your atom gets, the more energy levels you're going to need, because an energy level can only hold a certain number of electrons. 2 in the first shell, 8 in the shells after that. So potassium, okay, has 4 energy levels, 1 valence electron. You'll repeat the process for argon. You'll find that argon has 8 valence electrons and 3 energy levels. As you can see, argon, 8 valence electrons, 3 energy levels. And nitrogen is 5 valence electrons, 2 energy levels. So if you're talking about the periodic table, they're going to want to make sure you know about your metals, nonmetals, and metalloids as well. That's what this next section covers. It's giving us characteristics or properties, and it wants us to list whether it's a metal, a nonmetal, or a metalloid. All right? Hold on one second. Okay, so moving along, we're talking about metals, nonmetals, and metalloids. We know the properties of each. Metals are shiny, they have luster, they're conductors of electricity, they're malleable, they're ductile, they can be stretched into a wire. While nonmetals are the opposite. They don't conduct electricity, they're considered insulators, they're not shiny, they're dull, and they're usually pretty brittle. So when we're talking about dull, brittle, and poor conductors, we have to be talking about our nonmetals. When we're talking about something in between, meaning semiconductor, right, but also ductile, we're going to be talking about our metalloids. Because remember, metalloids are elements that have properties of both metals and nonmetals. And that leaves our metals down here at the bottom, shiny, malleable, high melting point. And some examples: sulfur, oxygen, silicon, boron. Let's see, for copper, you got copper, right? You can do nickel, iron, all examples of nonmetals. Which means hydrogen, right, since it's over on the far right side, all right, it's up at the very top, we know that hydrogen is a gas, which makes it a non-metal. And the reason why they're throwing that at you, because hydrogen's technically up here, guys. But hydrogen is the most simple element. It's the only place on the periodic table they could put it. But hydrogen clearly is not a metal. You know that. So hydrogen's not a metal. And the other tricky one is aluminum. See how aluminum is on the stair-step line? That should mean that it's a metalloid, but it's not. We know that aluminum's a metal. So it's the only one that's on the stair-step line that isn't a metalloid. So aluminum is a metal. So they wanted to make sure that you don't get those two confused, hydrogen and aluminum. Okay. Moving on to page 32 in our assessment. Leave this here for just a sec. Page 32 in our assessment. You need to know the difference between a mixture, a compound, 33, and an element. Page 33. So we have some examples here, and we're going to go through and we're going to mark all of our elements, compounds, and mixtures. Let's start by marking all of our elements. We know that because they're represented by a symbol, all right, or it's named the element. So Na is a symbol for sodium. That's an element. That's 21. Iron, Fe, is an element. Hydrogen, even though there's two of them, it's still just hydrogen. That's an element. Gold is an element. Au, we know gold is an element all by itself. Now let's go through and find our compounds. Compounds are two or more elements combined, two or more different elements combined, right? So we got CO2, that's carbon and oxygen. We got glucose, C6H12O6. Hydrogen chloride, HCl. And sodium hydroxide. Sodium, oxygen, hydrogen. Shh, thanks, guys. Please, please, please keep it together. We're almost done. Everything else is a mixture, like salt water, cement, Chex Mix, air. Not pure substances. They're mixtures. For this next one, 30 through 35, you need to have your chunks memorized. That is carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur. These are our 6 organic elements, all right? So you're only going to find these in organic molecules. Chunks, the acronym is CHONPS. If you just remember that acronym, then just look at your periodic table and find the letters that match. These are all the capital letters. These are the symbols for our 6 organic elements, all right? But the big one, guys, carbon. Don't forget about carbon. If it doesn't have carbon, it's not living. Everything living has carbon. All right, now breaking down chemical formula is something we've done a lot, but it's something that you guys, some of you guys need a little bit extra practice on. Let me autofocus real quick. So you need a little bit extra practice on this. We need to know the difference between a molecule, an element, and an atom. Now, a molecule is a group, right? It's a compound. So the big number in front, right? Your coefficient is going to tell you the number of molecules. The small number after an element is going to tell you the number of atoms, while the actual letters are going to tell you the number of elements. For example, in 4CO2, it's saying that we have 4 CO2 molecules. So in one CO2 molecule, right, we have 1 carbon and 2 oxygens. But we're not talking about 1 molecule. We're talking about 4 molecules. Therefore, it'd be 4 carbons and 8 oxygens in this 4 molecules of CO2. The 4 tells us the number of molecules. We count the elements, carbon and oxygen, that's 2. And then we count the total number of atoms. There's 1 carbon in 1 molecule, but since there's 4 of them, that's 4 times 1, that's 4. And then 4 molecules of 2 each, that's 4 times 2, that's 8. right? So your total atoms is 12. You can come down here and do the same thing. There's 2 molecules here, 3 different elements. And when you add up all of them, that's 1 Na, 1 O, 1 H, but there's 2 molecules of it. So that's 2 times 1, 2 times 1, 2 times 1. Add all those up, that's 6. 6 total atoms. It gets a little more complicated when you add parentheses in here. We know that from math, a parenthesis means that we need to apply this subscript to everything in that parenthesis. Everything needs to be included. So this isn't OH3. This is 3 oxygens and 3 hydrogens. But we have 3 molecules total. That means we have iron, oxygen, and hydrogens. That's 3 elements. We have 3 molecules. But if we have 1 Fe in 1 molecule, 3 molecules of this would be 3 irons, Fe. So that's 3 irons plus the 3 molecules of 3 oxygen. 3 times 3 is 9, plus 3 molecules of 3 hydrogen. 3 times 3 is 9. That's 9 plus 9 plus 3. That's 21 atoms total. And you have to be able to add up your atoms in order to tell if an equation is balanced or unbalanced. Balanced or unbalanced means on the left side of the arrow are the same amount of elements and number of elements. On each side of the arrow, that means balanced. If there's an uneven number or different elements, it's unbalanced. So look at this example here, number 39. Easiest way to do this is to write out the elements you have. So in this, we have iron, sulfur, and oxygen. And you're going to write it out for both sides of the arrow, Fe, S, and O. And then I want you to figure out how many atoms on each side of the arrow you have. Cool, you're right there. All right, so look at your iron. We have 4 molecules of 1 iron. Since there's nothing after Fe, it means 1. So that's 4 Fe. You look at S. Is there anything after S? No, but there's 4 molecules of FeS. So that's 4 times 1, that's 4. And then when you look at your oxygen, there's 2 oxygens, but there's 7 molecules of that. So 7 times 2 is 14. 14 plus 4 is 18, plus 4 is 22. That's 22 atoms over here. Then we look over here on the right side. We got 2 Fe2. That means there's 2 atoms of Fe, but there's 2 molecules. 2 times 2 is 4. Let's look at our sulfur next. So that's the one we're solving for. There's 1 sulfur here, but 4 molecules, so that's 4 sulfur. And then look at our oxygen. There's 2 oxygens right here, right? But 4 molecules of it. So that's 4 times 2, that's 8. But look at the other O's over here. There's 3, right, times 2. So that's 6 oxygens over here and 8 oxygens over here. That equals 14 oxygens. They equal. This means that it's balanced. You have the same number and type of element on each side of the arrow. Now, when you come down here and do the same thing, you're going to find that these numbers don't match. This problem is unbalanced. You'd have to repeat the same step you did right here. Just do it down here so you can see for yourself. You've got your carbons, your hydrogen, your oxygens. On this side of the arrow, your carbon, hydrogens, and oxygens of this side of the arrow. When you add them up, you find out that they do not match. Okay, 41 and 42. It just wants us to figure out what number is missing. And we know that the law of conservation of matter, the law of conservation of mass, heck, the law of conservation of energy says that things cannot be created or destroyed. They're just transformed. Energy, all right, elements, matter cannot be created or destroyed, just moved around. So if you end with 67 grams of something, you had to start with 13 plus 54 grams of something. Add up to 67. Over here, if you start with 18.5 and add 6.5 grams, you're going to end up with 25 grams of a substance when you're done. Real simple. It just wants to make sure you understand the law of conservation of energy, the law of conservation of mass. Now, chemical and physical changes in your body. Remember, a chemical change is something that undergoes a chemical reaction. You do not have the same substance after. While a physical change, it doesn't go down a chemical change. It's still just the same substance, just moved or cut or broken. So when you're eating a slice of pizza, a chemical change that would happen is your saliva. That's a chemical change inside your mouth. It starts to break down. All right. Also, your stomach acid. All right. The physical side would be you chewing, swallowing. You're not actually changing the food when you do that. You're just moving it around, making it to a smaller substance so you can break it down easier. When you burn a piece of paper, you can smell it. You see light being produced, and you now have a new substance left over. So these are all signs of a chemical change taking place. For 45, 46, and 47, you need to know your density triangle. Density equals mass divided by volume. All right? You can draw your little triangle for that, but it's just M up top, V down here, D on the left-hand side. So if you have 450 grams at 90 milliliters, you simply do the math. Mass divided by volume. 450 divided by 90 equals 5. And you take both units, gram / milliliters. And because it's greater than 1 gram, it's going to sink. Remember, anything more than 1 density will sink. Anything less than 1 will float. Substance 2, 35 divided by 70 equals 0.5 grams per milliliter. This is going to float. And 24 grams divided by 12 milliliters is going to equal 2 grams per liter. This will sink. It's just your density equation, guys. Very easy. Remember to use your triangle in case the STAARS test doesn't give you mass and volume, but instead gives you density and or mass and volume. And you need to find the opposite. You need to either find mass or volume. The very bottom, guys, your answers will vary drastically, but you're basically just drawing a food web, all right? So your answer's going to draw it, but you're drawing a food web, all right, food chain or energy pyramid, and then you're going to describe the flow of energy. So we'll just do a food chain. Actually, we'll do a food web because it's a little more complicated. So you need to draw some producers. You need to draw some consumers. You need to draw some primary consumers, secondary consumers, maybe some predators. Maybe some insects that are consumers, like spiders. Okay. So in a food web, you're going to have arrows showing where the energy is coming from. Where is it going? So it comes from the sun. Lots of animals eat this producer, this flower. All right? These animals are then eaten by other animals. Sometimes insects are eaten by other insects. And you'll see that there's lots of interconnecting webs. Lots of interconnection shows the diversity in the food chain here. Lots of animals have a pretty diverse diet, and so we're showing that here with a food web. Okay, and the description of this, guys, is it starts with photosynthesis, right? Starts with the sun. It moves to plants. Those plants or things like algae, things that create things, are then eaten by our consumers, right?
sometimes smaller consumers, and then those consumers are eaten by bigger consumers. And eventually, it's going to end up in an apex predator, or it's going to end up on your plate. But energy is lost throughout this entire process. You start with 100% of the energy from the sun. You lose energy as you go down because the plant is going to use some of that energy to grow. Then it's going to get eaten. That animal that ate the plant is going to use some of that energy from the plant, but then that animal is going to get eaten. So energy is lost as you go all the way through. By the time you get to the very top of a food pyramid or the very bottom of a food web, you're only touching maybe 5 or 10% of the energy that actually came from the sun. The rest of it has been used on survival, reproduction. Okay? Good. That's 32 and 33 assessment.